Okay, ladies and gentlemen, what I want to do today is start off by going through the examples from your worksheet. Each of you have shared your work. What I want to do is to try to give you some tricks for working through these types of problems. So first of all, with this one we are given silver gaining one electron to form silver atoms versus here nickel 2 positive to gain 2 electrons in order to become nickel. How come you need to switch this one around?
Because it's lower on the table.
Exactly. So if it gives you 2 reduction reactions, you have to use your data table in order to figure out which one of those chemical reactions is actually higher on the table than the rest. This one is going to become your oxidation reaction because you need something to lose its electrons in order for the silver to gain its electrons. One thing I want to make note of, because you do not have to do this, but I want to make sure that you know in case you were asked to do this. If you were asked to do a net ionic equation with this particular reaction, what would I be asking you to do?
You would have to put Ag positive plus Ni, and then, I don't know, you have to like balance it out too, and everything.
Okay, if you take a look at this, I'm just going to erase this one so that it is out of the way for you. If you take a look at the number of electrons lost and the number of electrons gained, it's not the same. 2 electrons lost here means that you need 2 electrons gained here. What are you going to do to this top reaction? Multiply by 2 so that you have 2 parts ions, you have 2 parts electrons, you have 2 parts silver. You do not change this number. Okay, you leave it as is. If I were to ask you for the overall or the net ionic equation, that means that I want you to add these 2 reactions together and give me the overall equation. For example, 2Ag positive plus Ni is going to give you 2Ag plus Ni2 positive. I don't need to show the electrons because if I lose 2 electrons and I gain 2 electrons, overall it cancels out. And then, yes, you add these 2 voltages together. The anode is the nickel because it is the site of oxidation. The cathode is the silver because it is the site of the reduction. When you write out your cell notation down here, make sure that you start off with your oxidation equation. Nickel loses 2 electrons to become nickel ions. The silver ions gain the electron in order to become silver. It basically tells you a story of the transfer of electrons. Let's look at the next one. Just make sure that I have it in the frame here. Yes, I do. You had the choice between aluminum versus iron. How did you know which one was going to be the anode and which one was going to be the cathode? Okay. In this case, you could definitely write out your half reactions in order to figure them out. But there's another trick to this. Makes the work go a little bit easier. Any suggestions of what that trick could be? Okay, well, I'll show you that trick later then. I need the table up on my board. I need to finish recording these answers before I put it back on the board. Okay. Over here, we have Michael's work, I believe. Okay, so it starts here and it ends over here. Okay, it's in the screen. Good. So Michael, how did you know that this is going to be the anode?
Because the number was lower
Yep, definitely.
than the AU.
Mm-hmm. So the anode is going to be the lead and the cathode is going to be the gold. What should your cell notation look like?
It didn't ask for a cell notation.
Okay, so you have your oxidation, which is lead to Pb2 positive, double arrow or double line Au3 positive to Au. Okay, so start off with the substance that's losing the electrons. Show what's made after it's lost. Show where the electrons go. And then the last thing in the cell notation is what forms as a result of gain of electrons. Onward to here. Angle that down a little bit. Okay, we have this reaction here. I really like that this person, who did this one? Sydney. You are using your square brackets to identify oxidation reduction. This set of questions is a lot different than the first set. In this set, you are told this is the redox reaction. You do not get to manipulate this and come up with your own oxidation and reduction half reactions. You are told that it goes from Ca2 positive to Ca, and that isn't that a reduction? If it goes from 2 positive to 0? If it goes from -1 to 0, that one should be an oxidation, which means that we're going to have to flip these. So we should have Ca to Ca2 positive plus 2 electrons, which will give you a positive voltage. This one would have been the correct one. So if I add these up, I should get 3.61 volts. Okay. You're not sure how I got that?
Ca2 positive is Ca2 positive is the redox, right? What's Ca? What's Ca?
Calcium?
Okay, and that's the reduction, right? Redox?
Okay, so you start with Ca2 positive and you're going to calcium.
Yeah, so that's the redox.
Well, this is totally a redox reaction. What I'm asking is if it is a reduction or an oxidation equation. Ca2 positive to Ca.
Is reduction.
Okay. And then I negative to I2 has to be oxidation.
Because Ca is -875. She should know. And if it's reduction, it doesn't flip. So
Correct.
So this should be negative.
Oh yeah, I see. I did something in my head. Sorry about that. Yep, I see what you're saying.
And this should be
Okay, so this one, so it was just labeled incorrectly up there. Okay, all right, now I'm a little bit less confused. Because in my head I am thinking, well, wait a minute, that should be a spontaneous equation. Okay, which means that this one is fine. And you should have negative.
This one should be negative.
Okay, now that makes more sense. It was just this part. I was wondering why that was turning into a spontaneous equation because I got non-spontaneous as well. If you use the oxidation number trick, it can help you identify if this part is reduction or oxidation a lot faster. Okay. What I tried to do over here, try not to run you over, is show that method here. So I have the H2S, oxygen gives me water plus sulfur. I assigned everything an oxidation number. Then I showed a change in the oxidation number and identified the process. Then it was a matter of finding these equations. What made this one a challenging question was that we had cancellation out of hydrogen ions. Because this is a net reaction, it won't show the hydrogen ions in here at all. That can make it challenging to find the half reaction on your table. So when you do this, you can see the H2S to S hydrogen ions and electrons will give you a negative voltage. Your oxygen plus hydrogen give you water. There's a positive voltage. An overall positive voltage tells you by definition that this is a spontaneous chemical reaction. If you do this method of identifying which one is the reduction and which one is the oxidation, it makes this process a lot easier too, because you start off with the oxidation, you show what happens after it loses electrons. Then you go to the reduction side, which is oxygen gaining 2 electrons in the formation of water. Question 5D. I have to reposition the screen a little bit here. There we go. Okay, so again, we have the identification of the cathode here. Instead of saying redox, we're going to say reduction, because redox is reduction plus oxidation.
I always mix up on the wording.
That's okay. I just want to make sure that when we have the answers, we have the correct wording. So again, you could do your oxidation numbers up here, and you see that the oxidation number is going from +1 to 0. So that's reduction, which makes that side the cathode. Okay. The oxidation is the bromine system here. The nice thing about using the brackets is it makes it easier to do the cell notation. So, it's not spontaneous. Technically, if it's not spontaneous, you would not do a cell notation. But that's okay. If you want to do extra work, I'm happy. All right, so Connor, you decided to change your answer to your question. What made you change?
They told me I did it wrong.
Oh, whichever one's oxidation.
I still really don't know.
Okay, so we have +2 over here to +3 over here. So that is oxidation. 2 positive down to 1 positive is going to be reduction, absolutely, which means you've got your equations here. Yes, positive and positive, so you will definitely have a spontaneous reaction. And then you have your cell notation here.
The only problem with that is that he has Cu instead of Cu positive, and the voltage should be 0.62 instead of 0.4. That's the only reason why it was wrong.
Okay.
The wrong was wrong, it was just the number.
Okay. This was also an unfair question because these half reactions were not both in the table. And that is definitely not a very fair thing to do. But I don't have Cu2 positive to Cu.
0.6.
But Connor didn't get it. So that's why he used the 0.34 here. So he still showed his work. I did have one professor in a second-year chem course who, because I didn't have him in the first-year university course, I did not know that we had to have a set of formulas memorized. So when I wrote the first exam for him, I didn't have these formulas for polyatomic ions memorized, and I left a question blank. He said that even if I would have showed work with something, even if the formula for the chemical was not correct, I could have got some marks because I would have been able to show the process. So not quite the correct voltage over here because it's Cu2 positive to Cu. However, you're still showing your logic here. I'm going to pause the video so that I can hook this back up to the smartboard. What I want to do is show you a few shortcuts using your standard table of reduction reactions in order to help you tackle questions like this. It will give you a little bit more confidence in making the decision about whether or not something is spontaneous or not spontaneous. Do you remember talking about agents?
Yes.
Okay.
Yeah, my agent called me last night.
All right. We have reducing agents. And we have oxidizing agents. How do we know what substance is a reducing agent and what substance is an oxidizing agent?
The one that
Whichever one is going under oxidation is the reducing agent.
Okay.
or the one that gains electrons and loses.
Okay, if something is being reduced, what agent is it?
It's an oxidization.
Oxidization agent. Versus if something is being oxidized, it is a reducing agent. Okay, please locate iron 3 positive to iron 2 positive on your data table. If I read this table from left to right, it is a reduction equation.
So it's oxidation agents on the right.
Michael? If I read an equation from right to left, it is an oxidation reaction. In this case, if I read the equation from left to right, is iron 3 positive an oxidization agent,
Yes.
or is it a reducing agent?
No.
It is an OA. If I read from right to left for something like copper, is copper a reducing agent or is it an oxidation agent?
Is it oxidizing agent?
Sorry, oxidizing agent or a reducing agent?
It'd be a reducing agent.
It'd be a reducing agent. Think back to the last couple days. How did you decide which chemical reaction was going to be the reduction reaction and which one is going to be the oxidizing?
Gain or loss of electrons.
Okay, yes, that's the definition. But if I had two equations, like I originally did over here with the silver and the nickel, how would I know which one had to flip around, Taylor? So whatever reduction reaction was higher on the table is going to be the reduction reaction. Whichever one is going to be lower on the table is going to have to flip and become the oxidation reaction. Okay, well, we know on the left-hand side of a chemical equation we have OAs, and we know that on the right-hand side we have RAs.
So oxidization agents, they flip?
Oxidation is when you read from right to left.
Okay.
So if I want to write out this down here as an oxidation, I would have to write out Cu to Cu2 positive plus 2 electrons.
So you read reductions left to right and oxidizations right to left?
Reduction is left to right.
Yes. And oxidization is right to left.
Oxidation is right to left. Yeah. So you might want to label this on your table somewhere.
Find it.
Oxidizing agents, OAs, are on the left-hand side of the table. Reducing agents are on the right-hand side of the table. I'm going to use some of the work that we did on the board as examples. Find your silver reaction and find your nickel reaction for question 1A. I need to make this smaller so that I can see both. Find the silver reduction reaction. It's right here. Ag positive is the OA. Find nickel. Down there. What do you notice about the position of silver ions, or the OA, compared to the RA? OA is above the RA. Let's test it out with Michael's question in part D.
I'm still confused from that stuff.
These are just tips and tricks.
In Michael's question, we saw that the reduction reaction was Au3 positive to Au, and on the anode we had lead losing 2 electrons to form lead-2 positive. Find those two equations on your data table.
Lead-2 positive. Au3 positive.
Found them.
Let me guess, oxidation agents always occur.
Is the oxidizing agent higher than the reducing agent?
Never. No, wait, yes, it's the opposite.
Okay. Let's try it with Sydney's question, question 5A. Question 5A. If the calcium is reduced, that makes it an oxidation agent. If the iodine here, iodide, is oxidized, this makes it the reducing agent. Please find those on the table. I'm going to need to zoom out a little bit more. Take a look at the position of the OA and the RA. The RA is above the OA. This particular chemical reaction is not a spontaneous reaction. Let's test out OA and RA position with the one that I did.
No, that was too confusing. Thank you.
Is the oxidizing agent above or below the RA?
Above.
It's above.
When it's
This is a spontaneous reaction. Spencer's question, 5D.
I swear, that's the most perfect one.
Find that on your table. Find the OA. Find the RA. What do you notice about the position of the OA and the RA?
Oxidation's lower.
It's not spontaneous. We can come up with a generalization that will help us identify right away if this is a spontaneous or not a spontaneous chemical reaction.
So if the reduction is higher than the oxidation, it's spontaneous.
If
The agent, yes.
So if you're talking about the reduction reaction,
I mean
yes.
the reduction agent.
If the oxidizing agent is above the reducing agent, it is spontaneous.
So if the reduction reaction is above the oxidation reaction, it's spontaneous.
Correct. So if the OA is above the RA, that chemical reaction is spontaneous. If the RA is above the OA, then it is not spontaneous. You could use this in a couple of ways. For example, we only had to do a lot of the work for this assignment from yesterday if it was a spontaneous chemical reaction. So if you can identify your oxidation and reducing, or if you can identify your oxidation and your reduction, that means you can identify your RE and your OE, go to the table, take a look at the positioning of the two, and then right away you can determine if this is a spontaneous or not a spontaneous chemical reaction.
Will you do anything if we spelled spontaneous? Yes.
You fail.
Chemistry 30.
So if you spelt it wrong,
We're not gonna have to worry.
if you spelt it wrong, you're done. If anybody else spelt it wrong, they're fine.
Yeah, it's
Oh.
no pressure from you.
See what happens when you fold my receipt up into a little teeny tiny square? I'm just kidding. No.
I just won't sell you groceries anymore. No. Just kidding. I'll get fired.
Oh, okay. What is important here is that you can identify whether or not it is spontaneous. It is not important if you can spell the word. I should be able to kind of sort of figure out what the word is.
It's spontaneous.
Just like on our final exam, making sure we have the right information with moles is not that important as putting the mole symbol.
Maybe not so much in that case. All right, we are going to wash off the tables. We're going to need some soap and water and clean up the tables for the end of class.